Wiz, my man, today we talk fine-tuning embeddings. Now, is this the same as fine-tuning LLMs?
Uh, define the same.
Mm-mm. So the fine-tuning, is that the same?
Kind of. It can be. Let's
Okay,
say it.
okay, okay. And the embedding model that we're fine-tuning, is that really different than the large language models we think about?
It is. So an embedding model can be a large language model, but there is a difference. Yes.
Okay, but when we think about LLMs, we think about the chat style models. And what we're doing today is we're fine tuning a model that's very different from one of these chat style models. Is that right?
That's very true.
Okay. I think we have to go kind of deep into almost the embedding layer of our understanding today to really grok the patterns and what levels they're happening on. Is that a fair assessment of this kind of oft misunderstood concept of fine-tuning embeddings?
Yeah, I think we have to really embed ourselves into this space.
Yeah, I
Yes.
think it's going to take a little bit of time. So buckle up, everybody. Wiz, we'll have you back in a while as we continue the discussions. I'm Dr. Greg, and that is the Wiz. We are AI Makerspace. Welcome to our Wednesday YouTube Live event. This week, we're talking fine tuning embeddings, and this is all about understanding embedding models in the context of more complex LLM applications like RAG or Retrieval-Augmented Generation applications. So we're going to build one today. We're going to see how it performs out of the box. And then we're going to fine tune the embeddings. We're going to have a little fun. If you haven't had a chance to watch the 8-hour podcast on Elon and Neuralink that Lex Friedman did, you don't need to, because we're going to build a RAG system and answer all the questions we need today. And we're going to fine tune it to understand Neuralink and neural specific language. Let's get into it, everybody. If you have questions along the way, please do throw them into the Slido link in the chat, or potentially right into the chat. We should have some time for QA today. It should be quite a bit of fun today. We're going deep. Let's start embedding ourselves as we align our aim to the day. We really want to understand the purpose of embeddings and why we need embeddings to do retrieval for something like RAG. We also want to understand how we can generate synthetic data that allows us to do fine tuning. A little SDG for some fine tuning. Classic SDG. This is also one of the most common ways that you'll end up leveraging SDG as you build more and more complex applications, specifically in that early prototyping phase. And then we're going to build a RAG application to answer questions about this epic 8-hour podcast using the full transcript, and we'll compare performance against specific questions as well as against RAG assessment metrics. All right, so let's recall what the R in RAG stands for first. Let's talk about embedding models and how they're used to domain adapt our retrieval systems in RAG before we get truly embedded, almost to the point of embedding something right in the brain when we do our build a little bit later. All right, let's recall RAG as we really focus in on the R. LLM chat models often, they lie to us. It's not cool. The way we can help them avoid this is we can help them augment the prompt every time we ask a question by reference material. We can help them fact check themselves before they start generating an answer. We can provide reference, information, we can add it directly to the prompt. We can get, hopefully, better answers. And RAG as a solution can be broken into two core pieces. The first is dense vector retrieval, and the second is in-context learning. We're going to talk about the first part the most today, and we're going to leave the second part. We've talked about it a lot elsewhere, but to get kind of a big picture of what we mean here, consider what happens when you ask a question to a RAG application. You ask a question, that question is then tokenized and fed into an embedding model. The text representation from the question is then turned into an embedding representation in vector space. That embedding representation is then compared to embedding representations of your reference material that you've already embedded and you've already stored in a vector store. So we're comparing the embedding representation of our question to embedding representations of chunks of our text data in our vector store. We can find stuff that's close together or related or has the same meaning. This is the big idea. Because when we set up the prompt for our question and we say, hey, answer the question, but use this context. The context we provide is the semantically related, that is the same type of meaning as our question data that we can get from our reference materials. That is returned not in an embedding representation form, but rather in a natural language form directly to the prompt. And this first piece is the retrieval part. We're leveraging vector embedding representations. We're doing retrieval. We're putting the references into the prompt, into the context window. We're putting them in context. This is RAG, but it's actually just retrieval and augmentation before we do the final generation. And the generation, again, is with an LLM chat model, not with an embedding model. That's when we get our final answer. When we think about the R in RAG, we can kind of break down dense vector retrieval into two pieces, dense vectors and retrieval. And we can sort of go way back a little bit to some classic NLP ideas when we think about dense vectors and we think about embedding representations. So for instance, you could look at a chart like this and you could see some fruit, you could see some buildings, some sports, and you might say, well, where would I put the word apple here? And of course, we're going to put it at C. Apples go with bananas and strawberries and grapes. Or we could look at this example and we could say, well, where do I put the word cow exactly? Does it go by calf? Well, yes, but not right by it, because puppy is to dog as calf is to cow. And we got two axes, we got two dimensions. These two dimensions, maybe this one is age, maybe this one is size. It's just two dimensions, and we need more dimensions to be able to represent more complex words, more complex phrases. So when we think about word embedding representations, again, vectorized representations of words that show words being of similar meaning, we're going to need a lot more than 2D. We see a lot of embedding models that have many thousands of dimensions. Super important as we get into more and more complex language. One of the most classic examples, and this is from over 10 years ago now, was word to vec. This was a great article, was a great explainer on word to vec from Jay Alamar, and this is, of course, the classic example. if you're sort of doing the vector math and it turns out that king minus man plus woman is approximately equal to queen, it means that your vector space is doing a good job representing these types of words and the relationships that they have to one another. And when we use these kind of pre-trained models, these kind of pre-trained embeddings, we can actually do a lot of interesting things that help us perform better ultimately on downstream tasks. This is specifically what we're trying to do in a RAG context. We're trying to answer questions in a way that's fact checkable. We can actually leverage embeddings directly to help us with this retrieval and augmentation approach. So Word2Vec was kind of this classic, super old school way of thinking about embeddings. Today, we have lots of different embedding models, from OpenAI to the massive text embedding benchmark leaderboard on Hugging Face and many, many open source models all the time. There's many to choose from, but that's not really the point of today's talk. We want to really focus in on what the role of this embedding model is in this retrieval aspect of our RAG system. And in order to do this, let's sort of consider the retrieval process. We ask the question, we search the database for stuff that's similar, and we return the similar stuff. We can see this dense vector retrieval happening in a visualization kind of like this. And it's important, again, to note that when we ask the question, we're turning the question into an embedded representation. When we search the vector database for similar embedding representations, we're collecting those, again, in embedding space. But we have to eventually return back to natural language. And so we take our initial documents, we chunk them up, we take the chunks and we tokenize the chunks, and then we run them through an embedding model before we ever even store them in the vector database. So in the vector store, we already have these embedded representations sitting there waiting to go. And that's what allows us to do this comparison of the question through the embedding model and the documents through the same embedding model and compare the similarity. So we're kind of doing this interesting thing where we're going from natural language text space to embedding space back to natural language text space. And this is very important when we think about embedding models. It's almost like you're doing something just so you can do the calculation, and then you come back. And in fact, that's exactly what we're doing, because we can't calculate with text. We have to get it in a numerical, machine readable format. And we can kind of consider from first principles what embedding is really doing and what it means. Because one of the key things that's so confusing about embedding models is that we call them embedding models. And we can look at this by checking out simple definitions of these words. Embed, such a great word for today's event. If we look this up, it just means to implant an idea or feeling within something else. So we're sort of implanting the idea of words being of a certain meaning into a vector space. Or we can think about an embedding as specifically a mapping of one set onto another, a text natural language representation onto a vector or numerical representation, or to enclose the embeddings directly by this embedding space that we've created Or, of course, you could think of embedding layers as being quite enclosed as we map from one thing to another. So this word embedding is used in so many different ways and in so many different places. It's hard to really kind of get a handle on what exactly it is that we're doing. But it's helpful to then focus in on the application rather than getting too meta with embeddings. What we want is we want to embed representations of our data, of our raw source documents. We want to embed these so that we can search them later. And of course, that's exactly what we're doing here. But we want to do more than that when we're actually fine-tuning a RAG system. So let's go just back up a level real quick. One of the things that is the same about embedding models and any large language model is you have some input and you get some output. A good embedding model is one that generates embeddings so that the input and the output are close together in embedding space. This is how we should think about embedding models being trained. That is to say that the input and the output must mean the same thing. And of course, you can use fancy ways of saying this. You can say they need to have the same semantic meaning, but we're being a bit superfluous when we say stuff like that, because of course we're using text and we're assessing meaning. So let's see a couple of examples. Like, it's not that crazy, guys. It's like, can you generate embedding representations for, let's say, input? A person on a horse jumps over a broken down airplane. And output, a person is outdoors on a horse. These two things should be close in embedding space. So if our embedding model is one that can take in text, locate it relative to other text, we want it to be able to do this well with specific words. You see here, children smiling at and waving at camera. There are children present. These should be close in embedding space. And so on, right? Now, importantly too, these are sentence embedding representations. Whereas in the dog, puppy, calf, cow example, these were 2D word representations. So I want to bring Wiz up for a second. I want to just kind of talk about this. We've got like these huge embedding models, there are all these dimensions, but we can also look at the word level for embeddings, or we can look at the sentence level. But the sentence level also feels like it's kind of looking at the word level. In the examples we just saw with person and children and boy, I mean, first of all, is the easiest way to think about this at the word level? And then in practice, are we generally always using sentence level?
Yeah, so this is a great time to clarify, right? So we actually, when we talk about embedding models in 2024, we're actually talking about the token level embeddings. So this is typically actually a subword level token, right? So the idea is the same, where but we substitute the word for token. And when we use embedding models, like say from sentence transformers, what we care about is the total embedded representation of our sequence of tokens. The way we achieve this is hilariously simple, right? We take a token, a representation. Say there's 10 tokens, we get an embedding for each of them, and then we pool them together, either by using the average in each slot or the max in each slot, and that's it, right? So if we have an embedding model that produces like an embedding vector of size 728, right? We're just going to literally choose from each of the tokens, either the max, or we're going to average all of their values in order to combine all those tokens into one single embedded representation.
Okay, so the word means something. You got 768 dimensions of the word meaning.
Yeah.
And then if you have like another word in the sentence, you could actually just average these two 768 vectors.
That's right.
And it works.
It works pretty good. Yeah.
Oh.
Yeah, it works great.
Okay. And just to clarify, like when you say sub word, you mean like half of a word? You mean like,
like run and running, right?
Yeah.
Run and running. I mean, run means the same thing, regardless of if we have that ing on the end, right?
Right.
The act of run is, we all get it, moving our legs, going fast. That ing though, right? That we technically ning, but we append to that's how I think about subwords.
Or like embed versus embedding. Oh,
you know it.
Now I don't know. Are they the same? Are they different? But it's all about looking at the right level so that we can again capture the semantic meaning, capture just the relatedness of the meaning of the words. So run versus running. I mean, you're not adding anything. So why would you look at the word level for running? That's just silly, right? So, okay. Got it. Okay, so then we're going to be using sentence transformers today, but it's useful to think in this word token level as we sort of try to grok semantic meaning capture. Okay, cool. Wiz, we'll see you back in just a little bit. Let's get into, now that we have these embedding models, how are we going to use them for domain adapted retrieval? Again, the retrieval process shown here. When we're talking about domain adaptation, what we're talking about is generally domains or specializations where if you're not part of that club, if you've not been trained in that specialty, you might be like, what are you saying exactly? A lot of the words that they use can be highly specialized. Researchers famously do this in every department at the universities or at every conference around the world. But lawyers, doctors, all of these folks have very specialized language. Even the government has often specialized initialisms or acronyms that we can potentially put into this bucket of specialty meaning that in the end, the embedding model was probably not trained on from the beginning. And so when we have this specialized domain and we have data that we've tried to give the LLM access to in RAG, we can start to look at the next layer of actually fine-tuning the embedding model. Now, there are many ways that we can increase RAG performance. Many ways. How am I going to dial in my chunk sizes? How am I going to make sure I'm doing really smart search and setting up my data correctly? And there are a lot of really sort of easy ways to try advanced retrieval strategies. We're going to focus today on this fine-tuning of embeddings because it's quite an easy way to increase retrieval performance. Now, if you have an insane amount of data, or if it changes super often, this is probably going to be less cost effective, as you see on this kind of chart from Llama Index here. Kind of harder to implement, higher latency and cost. It can be, but if you're in an early prototyping phase, this can be a very, very powerful thing to pull out of your toolbox early and see if it makes a big difference. And you'll see that in our demo today. Think about what the retrieval system is doing. It's retrieving the right context based on your question. And so what we need is this idea of a question context input output pairing to do fine tuning. Now, recall, the point of an embedding model is to say this is close to that. So if this context gives me this question, then I'm starting to get along the path. Wait, did he say this context gives me this question? Yes, I did, because we actually need to generate hypothetical questions based on ground truth context. And here is where our good friend SDG comes in, where we take our data and we generate question context pairs so we can fine-tune embeddings. How does this look exactly, though? Well, if we recall that the whole vector store setup in the first place was splitting the docs into chunks, running those through an embedding model, saving the vector embedding representations, then we can say that let's just take the stuff that's in the vector store and start with that. Okay, so let's just say I'm going to start with the embedding representations that are already in my vector store. And then I'm going to generate chunks. And not even generate. I'm just going to pull them out. I already did this. I already got the chunks. I'm just going to specify the chunks that I've already created through the process of building the vector store. And then what I'm going to do is I'm going to take the chunks and I'm going to run these chunks through an LLM chat model. Okay, so this is a generator here. This isn't an embedding model. And I'm going to say, what kind of question would I be asking if I had this chunk? And so what I'll end up doing is I'll generate hypothetical questions. In fact, multiple questions for individual chunks, because many different questions might return the same chunk. And then I'll be able to have my question context pairs. And the way that this manifests itself in the fine-tuning process is if we've got our context chunks and we've got our generated questions, then what we'll do is we'll take our generated questions, we'll consider those as input. We'll take our context chunks, we'll consider those as output, and then we'll do some fine-tuning on our embedding model, and we'll tune the weights to be able to better understand and pick up, especially language that's quite specialized and not something that our embedding model has seen before. So what we end up doing is we actually create training, test sets, validation sets using these pairings of question and retrieved context. These questions are, again, synthetically generated. Wiz will walk us through exactly how this is working. And we're going to use a training technique that uses a slightly different loss function, which Wiz will also talk about, versus an LLM chat model training. And we're also going to do the actual training in a very similar way, minimize the loss function that we would see in any given fine-tuning context. So as we set up for our build today, we're going to pull from this epic pod that I have not had a chance to listen to, and we kind of wanted to do this last week, so we're going ahead and rocking into it, because this is also not just something that would take a long time for anybody to fully ingest, but it's something that's a great candidate for fine-tuning embeddings. There's potentially lots of jargon, lots of big words, very specialized domain, and quite a bit of data. So for instance, like if you look through even the chapters that are available in the transcript here, you'll see things like neural dust, neural decoder, neural surgery versus neural link surgery, and web grid. You'll see words that you're just like, what? And so here we are. What we're going to do is we're going to build out a domain adapted RAG application that dials in our embedding model with this Neuralink data. And we'll see, does linking the embeddings directly to Neuralink help us understand quicker, better, these big fancy jargon words? And I think you'll find that the answer is almost in all cases where you have something like this, yes, it works pretty well. Wiz, show us exactly how it works pretty well.
Oh, yeah. Okay, Greg. Thank you so much for passing it over. All right, so fine-tuning embedding models for RAG. Greg walked us through all the concepts, and now we're going to talk about some of the code. The code is pretty straightforward thanks to a number of powerful libraries. So this includes transformers, LangChain. We're going to get into it. So first thing we need to do is apply this nest async IO helper function. This is going to make sure that we don't run into weird async issues while we're in the Colab environment. And then we're going to use the dependencies from LangChain to get us kicked off. We're also going to use an unstructured today, since we're going to be dealing with an HTML file. And then we're going to use face as our eventual vector store. Okay. First things first, we need to go ahead and we need to get some data. So we're just going to retrieve the data from this GitHub repo. We're going to be using the Elon Musk Lex Friedman transcript. So this is available through Lex Friedman's site. All we did was download it and put it into the repo. All this is basically the way you can think about this, right? Is that we have some corpus of information in which there is specific language and specific terminology, and we just need to teach our embedding model, how it should respond or what it should respond as, right? So the idea is that we have a bunch of information that we are going to ask questions about. We have the advantage here of knowing what our use case will be, right? So what we're going to do is we're going to train the embedding model to pull up the correct, quote unquote, correct information from the actual, retrieve or potential set of retrieved documents by showing it questions and context pairs. So let's get into how we actually create this. Number one, we're going to just split. This is fully arbitrary. There's all kinds of optimization you could do in chunking usually. For this case, we just need lots of chunks. There isn't really a ton of specific optimization you can do other than making sure you're not, creating irrelevant or useless chunks. So we make the chunk size fairly large since we have a lot of text. We wind up with a total of 963 or so, documents. Then we're going to do this association game. This is necessary just to make the further steps seamless. So there is no point to this other than it makes the rest of the steps easier. Okay. So when we go to the create our documentation or our documents for training, validation, and test, you can see all we're going to do is we're going to use, only 300 examples for training, 150 for validation, and then, 50 for validation and then 50 for tests. So, again, this is just so that this runs in a reasonable time in the Colab environment. You could do much more here. You could train on 10,000, right? But the idea is fairly straightforwardly that we just need some number of chunks. And all these are right now are chunks, right? So we've created 963 total chunks, and we're going to pull, from 400 of those, the first 400, very importantly. Now, one of the optimizations that you're going to think about making is which chunks should you pull? Where should you pull them from? And when we look at, things like the technical report for the Snowflake model, there's a ton of different pre-processing you can do and post-processing you can do to make sure that those chunks and questions are high quality. But for the purposes of the Colab, we're just going to leave it with the first 300 items for training, and then validation is the next 50 and test is the next 50. The reason we're chopping off the tail here is that the tail of the HTML file is filled with rather useless information, and we don't want to train on that. Okay, so now we construct a fine-tuning data set. First things first, we're going to be using GPT-4o Mini just because it's good enough, right? All we need to do is create questions that are related to the chunks. The way we're going to do this is with this simple prompt. We're going to create n questions, questions which should be provided in the following format, right? In this kind of list format with this context as the rule. Now, you'll notice that we're creating question plural, right? So 2 questions in this case. And the reason we're going to do that is kind of the same reason you might think about, multi-query retrieval or these kinds of patterns that we're familiar with potentially through RAG, right? Instead of just saying this question is associated with this chunk, right? We want to say, here are the different questions associated with this chunk. That's going to help that embedding model understand that a particular chunk from multiple different perspectives. So again, if you want the notebook to take a little while longer, you can try this with like n equals 5 or n equals 10 or whatever it is that you happen to use. We're going to be using n equals 2 again, just to make sure that it runs in a reasonable amount of time in the Colab environment. Again, we're going to do all of this. All this is doing is making sure that we associate our chunks correctly for training later. So you're going to notice that we brought up this UUID, which we set up when we created our actual chunks here, and we're going to associate these things based on those IDs. Again, this is just to make the utilization of sentence transformers easier for ourselves. You could just as easily do this in a data, Hugging Face data set, but we're going to do this just to make our lives a little bit easier later on. And then we generate 300 instances of data generation, which is actually going to lead to 600 total questions, since we're doing 2 questions per. And then we're going to do the same for val and the same for test. And that's it. Now we're going to go ahead and save these out. You don't have to save them out, but it's useful if you want to. And then we're going to finally get into loading our model. So this is classic machine learning, like as classic as you can get, right? We are going to, spend all the first part of the notebook managing our data, collecting data, making sure it's in the right format, everything like that. And then we finally get into the part where the model, where we load the model. We're going to be using Arctic Embed Medium as our base model today. Again, this is just so it runs nicely in the Colab environment. You can use whatever sentence transformer model you want. This is going to work fine. We load it up. We load some awesome Torch utils and sentence transformer input examples. We create our examples. We create our batch size. Again, if this were a non-Colab environment, or you had access to like an A100 Colab environment, you might want to make the batch size much larger. But this works and fits well into GPU RAM, even on the free version of Colab. So that's great. And you'll see that it's not without results. We're going to create our data loader. So if you're familiar with the kind of the Torch flow of training, you're going to be used to this data loader. Basically, this is a thing that lets us pull training examples out of a hat whenever we ask for them. Very useful structure. We're going to use it here. Then we're going to use our loss. Now we're going to use this multiple negative ranking loss as our core loss, but we're also going to be using on top of it this idea of Matrioska loss. Now this Matrioska loss, if you're familiar with Matrioska dolls, right, which is these kind of dolls that are, I'll just zoom in a little bit here, these dolls that are kind of, very much stacked on top of each other. Sorry about the scrolling for you there, but the idea is that, when we have embeddings, right, they might be very long. So you might be used to say like OpenAI's ADA02 is like 1024 embedding dimension, right? So there are quite a lot of numbers in a row. Now what the Matrioska loss does for us, first of all, it lets us have a variable vector size. So this is just useful, right? If we're in some way limited or need to conform to a particular size, we're going to be able to do that with the Matrioska loss. As well, and this is really the fun part, it's going to kind of front load the most important pieces of embedding information at the front, quote unquote, the front of the list, right? So the beginning of that list. And that's how we're able to create this nesting doll of embeddings, where we're able to just chop off the back half, because the back half is not as, information rich as the front half. And so this is just to show you how straightforwardly you can implement this loss thanks to sentence transformers. This is the same thing that lets OpenAI give us variable length embeddings. It's really cool. So we add it, but the actual core loss is being used, of course, is the multiple negatives ranking loss. So we're going to go ahead and check that out in the code. It's, it is what it is. The basic idea here is that you'll remember that Greg said we needed examples of what should be close, right? Where we have this idea of quote unquote closeness when we're dealing with embeddings. So some sentences are closer than other sentences, right? The way that this multiple negatives ranking loss works is it actually lets us generate tons of negative examples by using the embedding retrieval, where we have a positive pair, and then we will sample n-1 negative docs randomly. So the idea is, if we have a data set that we've constructed, and that data set has positive examples, what we're going to be able to do is we're going to just pull from any other examples in our data set as the negative examples. And that contrastive learning is going to help us fine-tune and get better results quicker. So that's why we're using this loss, and that's why we've added Matrioska loss. There you go. Okay, so all of that, maybe and it's a similar-ish from the chat. Black Current asks, is it like PCA ordering dimensions by importance? It is a similar process. The conceptual process is identical, where we are ordering based on how information-rich each of the embedding dimensions are. Yes. Okay, so we talked about it. And the code looked complicated, under the hood. And, when we looked at the loss, okay, there's a lot of words and everything. But the implementation is, we create a list of dimensions, pretty straightforward. We create an inner training loss, which is our multiple negatives ranking loss. And then our full train loss is the Matrioska loss. And that's it. Then we're going to create the evaluator. The evaluator is going to be based on the information retrieval evaluator from sentence transformers. We're going to use this for our validation while we're doing our training. We're going to train this for 5 epochs. We could train for more epochs if we had more time. But this, makes it take just a little while in the notebook. So that's why we've chosen 5. We're going to do a manual warm-up here, and then we're going to fit our model. You'll notice that we're using the loader for our data loader and our training loss, which is our overall Matrioska loss, which is, has the inner loss of multiple negative ranking loss. We're going to output this to fine-tune to Arctic. We're going to show that progress bar, and then we're going to do an evaluation every 50 steps. You can see here that the training and validation loss don't get propagated up by default, which is fine. We can see the rest of our metrics, and there are a lot of them, and we'll see how that looks when we go to testing it out. So now that we are ready to, and that's it. Like that, of course, the data preparation was a bunch of steps, all these steps, and then training the model is just a few cells and culminates in a dot fit. Okay, so we have our model fit, and now we're going to evaluate it. We want to evaluate it in a particular way, and we want to evaluate things in a way that makes sense. So what we're going to do is create an evaluate function. We're going to evaluate by retrieving some context. And because we have a question that has a ground truth context, right? Every context that we have, we've created questions for. So there's a correct, a labeled set of data here, right? That shows us, hey, for this question, we should retrieve this context, right? So what we're going to do is basically just build that system to check for that. And how we're going to evaluate is by hit rate. So how often do we retrieve the correct context when we go to retrieve the context? That's it. All right. So we're going to go ahead and evaluate our model against the base version as well as text embedding 3 small, just to see the kind of improvement we can make and how close we can get to the closed source alternative that has many more dimensions and is much larger than our model. Okay, so first of all, when we use text embedding 3 small, we get a hit rate of Everyone loves to see it. 1.0, we get 100% hit rate. That's great. How about for our unfine-tuned model? Maybe not so good. We get a hit rate of 0.64. So remember, there's 100 documents in our test set. So this is literally, we retrieve 64 out of 100 correctly. So how does our fine-tuned model do, right? Remember, we only use 300, 300 examples here, and we get, you love to see it, all the way to 99, right? So this model is now almost as good as the Text Embedding 3 model, but it's open source, it's small, it's reasonable. I mean, you can't get much happier than that. So we've seen that in hit rate, or in an official metric, we do pretty well. Let's vibe check, right? So let's see how this thing actually does when we do the RAG with that retriever. So we're just going to create, we're going to rechunk our document so we don't bias it. We're still going to bias it a little bit, but of course we're going to rechunk our documents just to play it safe. And then we're going to create the base retriever version of our RAG chain, and you'll see that here. And then we can ask questions like, what is ayahuasca? I don't know. What is the difference between neurosurgery versus Neuralink surgery? Actually, pretty good response. What is neural dust? I don't know. What is a neural decoder? Decent response, right? And who got Neuralink surgery? The first human being to receive Neuralink surgery is referred to as Noland. So that's cool. Okay, so the vibes are not great. They're not awful, but they're not great. Let's try our fine-tuned model. What is ayahuasca? We get a detailed response for about ayahuasca. What is the difference between neurosurgery and Neuralink surgery? We get a more detailed response. What is neural dust? We actually get a response, and that response is quite good. What is neural decoder? We get about the same response. And then who got Neuralink surgery? We get both pieces of information about this person, their first and last name, which is super hype. Okay, so that vibe check, the vibes feel better. How about the actual evaluation? We're going to use RAGAS to evaluate. You've seen it before, so we're not going to belabor it, but first thing we need to do is create a synthetic test set, which is going to include questions, ground truths, and some context. And then we're going to go ahead and use that to evaluate our models. We'll see that our initial model gets a context precision that's kind of low, faithfulness is kind of low, answer relevancy kind of low, and context recall kind of low. And how does our fine-tuned data set or fine-tuned embedding model RAG pipeline do? Way better, right? We went from the 40s to about the 80s into the 90s. And this is the, especially looking at the context metric, right? This is the power of fine-tuning those embeddings. Again, only 300 samples. We trained for 5 epochs with very small batch size, and we're able to get this kind of improvement on our corpus. So this is the power, quote unquote, of training embeddings. This is why this is table stakes, right? Something we're always going to want to do when we try to figure out how do we improve our RAG system, in a way that's meaningful. Okay, so before I send you back to Greg, we got to say it. Please don't forget to subscribe and ring the bell notification. It lets you know when we go live. We're live every Wednesday. I love doing this. So thanks so much, and we'll head back to Greg.
Yes, thanks, Wiz. That was an epic walkthrough. And just in case you guys didn't catch the fine point on the end, is if you are doing this in sort of a company capacity and an enterprise capacity, one of the things you can do is you can wrap this whole thing in RAG assessment, which requires some additional synthetic data generation and some additional work. It's all in the notebook today, and I'm not going to read you this slide, but the point is that of all the 4 metrics, there's one called context precision. And context precision is one that helps us evaluate whether all of the relevant items are present in the context when we ask a given question. And so if this is very high, it means all of the relevant chunks are appearing in the top ranks of context. And in general, this is exactly what we're trying to improve when we fine-tune embeddings. So we see this domain adaptation can have a very big impact on your performance. And this is a great result to sort of demonstrate that your application was successful and is on the path to great improvements. Okay. With that, we are ready to wrap up. And today we can kind of conclude a couple of things, namely that this idea of embedding models is one that is kind of hard to grok. It's going to be something that is elusive to you for maybe ever in some sense, but it should start to become clearer the more you start thinking about embedding models versus embedding layers versus embedding representations. And you can kind of put this whole thing together in a way that is going to be applicable, not sort of across the board, but in various different build modes you might be focused on. At the end of the day, the embedding model, the one that we're going to use in RAG applications, is about being able to align the meaning of input and output, whether it's one sentence, then the next sentence, or it's a question and relevant context, or it's one word and then a similar word, or if it's one sentence about the boy on the beach and one sentence about a person on the beach. Input and output want to be close in embedding space. The embedding model allows us to cast stuff into embedding space. And when we take this model and we leverage what we already have by building out the dense vector retrieval system, we can actually do the fine-tuning with just a little bit of SDG to generate those hypothetical questions, getting our question context pairs and doing some good old-fashioned machine learning to up our game. So we've got some great questions in the chat, and I think we can go ahead and get into Q&A directly now, Wiz. I'm gonna go straight to the chat, but I want to actually ask just one question first that I think is a very common one, and that is, we use a Snowflake embedding model. Is there any reason to, when I'm building applications, use like the Snowflake LLM? Is that going to perform better if I pair the snowflakes or the Mistrals or, the sort of embedding an LLM chat model from the same manufacturer? Is this something that's worth thinking about?
No, no, it's not. It's drastic, but the way I think about this is like, if Snowflake created a vision model, right? Should you pair that vision model with their text model? And I think in that case, it doesn't make any sense, right? One's for vision, one's for text. What does pairing them even mean in that case, right? They don't share inputs or outputs. It's the same thing with embedding model. Now, they do share the same kinds of inputs, which is going to be sequences of tokens. But other than that, they're intended for totally different purposes. And the way we leverage them, specifically in RAG, means that we go back to the domain of text. So the thing that you want to optimize for is the retrieval model or the embedding model that best retrieves information from your vector database. No bearing at all on the model choice. They're not linked in any way other than they were created by the same company.
Okay. All right, so we've got some great questions, and I'm going to start off with first question from Anonymous. What is LLM to VEC? And I think like this is highly upvoted too. And just to get everybody on the same page with this question, this says, hey, large decoder only LLMs are the state of the art, but the community is only slowly adopting these models for text embedding tasks. In this work, we do exactly that. Forget word to VEC, it's LLM to VEC. What do you think about this, Wiz? Should we be paying attention?
What I think of it is maybe, less interesting. Is it something to pay attention to? It's certainly, why not? I mean, yeah. It's something that I think is good to explore, let's say.
So what is it exactly? Like, what's going on there? What are they trying to do?
Well, it's like imagine if we souped up embedding models all the way to the moon, right? Like,
okay,
they should perform better. And the answer
Sounds
is they
legit.
should perform better. But as we saw on our exact use case, our very small, embedding model in comparison performed pretty good, and at the fraction of a cost, right? So it's just going to depend on what your use case
So
is.
this is basically kind of, we're doing the unsupervised pre-training in any given embedding model context, just as we are in any LLM context. This is kind of what, doing enough unsupervised pre-training to build the, all words embedding model, or like what's going on here? I don't.
Yeah, it's the same thing as it's the same thing we did when we originally created the decoder only stack. And the question is, can we add so much data that it becomes good at these embedding tasks or encoder only traditional tasks? And the answer is probably.
More data. Okay, yeah. But do we need the everything machine to build task-specific applications? No, and we don't need the everything and everything else machine either. But sounds pretty cool. And if you guys want, keep upvoting it. Maybe we'll take a deeper look at it. Okay, next up we've got, can we fine-tune embeddings to create vectors where specific values will represent desired features? Can you sort of align it with classic ML like this?
Yeah. Kind of. I mean, no is the real answer. So this is a great explainability question, XAI question, right? But in current forms, sorry, no,
Okay.
not in a useful way.
Okay. Next up, how can we identify which value of an embedding correlates with which feature in human language? Okay, here we are. let's attack it from a different angle here. Explainability of embeddings.
We have no idea. When I say we have no idea, that doesn't mean literally we can't have any idea ever. It just means that the language model might not align to the human understanding of properties in the exact same way. So, similar to when you have a very large set of features in traditional ML, like it can be difficult to parse what access that these say PCA, right? So we had PCA earlier, right? PCA is a great example where it's just like, well, we're gonna bake it down into this other set of features, but what do those features now mean? And the answer is much more difficult to answer, right? It's the same thing for these kinds of embedding models.
Okay, I like that. Yeah, okay. So we're sort of doing the boiling down when we're doing the training of the embedding models. Kind of like, okay, all right. Okay. Wiz, when you did the training, loss didn't seem to change a lot. Why?
Loss didn't change at all, technically, because it was not reported. The truth is that on this simple example, we don't really need a lot of data to make it better, so we plateau very quickly.
Okay.
Yeah.
Cool.
That's it.
Built an app with RAG. Should I start with fine-tuning embedding? Thank you for asking this question. Should we start? And if so, how much is this going to cost me, man?
You should not start with fine-tuning embeddings before you do prompting. Okay, so we're still living in a world where the first step is prompting, and then the second step might be fine-tuning embeddings. It is extraordinarily cheap compared to fine-tuning the generation model, and it's not too cost impacting overall, because you don't need tons and tons of examples. So even the data creation is relatively inexpensive, and it can be offloaded to LLMs, so you can use SCG here. I would say the cost of GPUs can be worth it if you're in a very specialized retrieval domain where you have kind of language that is non-standard or unique to your use case.
Do the prompting, maybe mess with some chunk sizes, but yeah, it should be early on in the game, though. If you have again, not if you have all the data in the world and you want to fine tune it on all of it, but if you have like a representative sample of data that's pretty interesting and difficult, and again, ask your specific questions and know what you want to be good at, right? And if you can't answer it, then try a little fine tune, and maybe it'll be like, oh, okay, yeah, neural surgery, got it, Okay, can we rapid fire here real quick? Are there multilingual embeddings that we can sort of do fine tuning on?
Yes.
Do you have recommendations?
Cohere has good multilingual embeddings as well. I think there's, if you look up kind of the MTEB, I believe they have a tab. I'm just verifying they have a tab that includes multilingual.
Multilingual, yeah.
It is possible. I would say for right now, you're gonna want to stick with things like, I think Quen is decent. The magic of embeddings is that as long as you can represent the tokens to it and those tokens are in the corpus, then you should be able to fine tune it. Yeah.
Okay. And final upvoted question from Kay saying, if we have stored embeddings of millions of docs in a vector DB, can we swap the underlying embedding model with any other state-of-the-art embedding model?
Not without redoing all of that embedding.
That's right.
So your embedding model, the embedding vectors are unique to each embedding model.
Yeah.
Period. Yeah.
Once you've gone into the bed, you're laying down in the bed, you have to get up out of the bed and go find another bed to embed. Yeah. Okay. Yeah. So you can, but you're going to have to re-embed. And that's one of the things that if data is changing all the time, because we don't want to have to re-embed constantly. So yeah, like, try not to have to do that a lot. Probably is going to be the most cost-effective strategy. All right. Great stuff, everybody. Thank you, Wiz, for walking us through that. That was an epic demo today. And everybody, it's time to wrap up today's event on fine-tuning embeddings for better retrieval. If you like this session and you want to keep up with what's going on in the community, please join us in Discord. We're at over 1,600 members now. We'd love to see you jump in and start building, shipping, and sharing with us today. If you're thinking about accelerating your LLM application development, we recently launched our cohort number 4 of the AI Engineering Bootcamp, and the next one is going to be coming up in November. If you sign up early, then there's actually a 10-week sequence of onboarding materials we've created called the AI Engineering On-Ramp to give you a little bit of transformer background, of fine-tuning background, and of alignment background each week. And this is something that you can start engaging with right now. If you're interested in getting out ahead of cohort 5, put in your application today. And if you have any feedback on today's session or ideas on what you'd like to see in the future, please let us know in the feedback form directly. And until next time, everybody, keep building, shipping, and sharing, and we will certainly do the same. See you next week on Wednesday. Bye, everybody. Have a great week.